Applying Kirchhoff's laws. Here we have a circuit involving a cell of EMF E and internal resistance 2.5 ohms. It's in series with a 50 ohm resistor and a 10 and 30 ohm resistor in parallel. We have a voltmeter across the parallel part of the circuit, and we have ammeters here, here and here. We're told ammeter 2, this one, reads 0.45 amps, and asked to calculate for A the reading on the voltmeter. Well, for this we can use Ohm's law that V equals IR. Putting in the figures gives a reading on the voltmeter of 4.5 volts. For part B, we're asked for the reading on ammeter 3, this one. Well, again we can use Ohm's law. Current is voltage over resistance, giving a current through ammeter 3 of 0.15 amps. Now we're asked for the reading on ammeter 1. Well, here by Kirchhoff's first law, that the current through ammeter 1 must equal the current through ammeter 2 and the current through ammeter 3. Putting in the figures for ammeter 2 and ammeter 3 means ammeter 1 must have a reading of 0.6 amps. So 0.6 amps come along here, 0.45 go this way, and 0.15 go this way. In D, we're asked for the potential difference across the 50 ohm resistor. Again, using Ohm's law, voltage is current times resistance. We've found the current of 0.6 amps, the resistance 50 ohms, means the potential difference across the 50 ohm resistor is 30 volts. For part E, we're asked for the terminal potential difference of the cell. Well, the terminal potential difference across here must equal the potential difference across the resistor here plus the potential difference across the parallel section. So the terminal potential difference is the 4.5 volts we lose across the parallel section plus the 30 volts across the 50 ohm resistor, meaning it will have a value of 34.5 volts. Now we're asked for the potential difference across the internal resistance of the cell. Well, again using Ohm's law, we know the current is 0.6 amps, it has an internal resistance of 2.5 ohms, so a PD of 1.5 volts. And for G, we're asked for the EMF of the cell. Well, the EMF, by Kirchhoff's second law, must be the sum of the potential differences around the circuit, and we had a PD of 30 volts across the 50 ohm resistor, 4.5 volts across the parallel section, and 1.5 volts across the internal resistance of the cell, meaning the EMF is the sum of these at 36 volts. Here we have a simplified version of a car circuit involving two sources of EMF. There's the 15 volt supply with internal resistance 0.6 ohms. This provides electricity while the engine is turning. And we also have the 12 volt battery with negligible internal resistance. The resistor down here is representing the resistance of the components being operated at the time, which could involve windscreen wipers, lights, radios, and so on. The value of this resistance will change. The charger here and the battery are in parallel, and so the terminal potential difference of the charger must equal that of the battery at 12 volts. So there must be a potential difference of 3 volts across the internal resistance of 0.6 ohms. So we can find the current through here. The current is equal to voltage over resistance, meaning there is a current from the power supply here of 5 amps. I'm going to mark that on my circuit here. When the starter motor is operated, the load resistance down here has a value of 0.4 ohms. So now, again using Ohm's law, we can work out that the current down here must be 30 amps, which I'll mark on the diagram. Using Kirchhoff's first law, if we have 5 amps coming down here to this junction, 30 amps leaving the junction, we must have 25 amps coming into the junction at this point. So in this case, with the starter motor being operated, both the charger and the battery are supplying the components. When the engine's running and there are fewer components operating, the load resistance here rises from 0.4 ohms to 6 ohms. The terminal potential difference of the charger must still equal that at the battery at 12 volts, and therefore there must be a PD of 3 volts across the internal resistance still, meaning we still have our 5 amps coming down here. Now the current through the load resistor is given from Ohm's law of our 12 volts over now 6 ohms, meaning the current down here is 2 amps. So now there's 5 amps entering this junction, 2 amps leaving the junction here, meaning there must be 3 amps coming along here, and this serves to charge up the battery. Here we have another circuit, and we're asked to find the readings on ammeters 1 and 2. Well, assuming the current goes anti-clockwise round here or round here, we can then put an arrow at this point, and this will be current 1, the current that goes through ammeter 1. We can put an arrow at this point, and this will be current 2 that passes through ammeter 2. If current 1 comes down here and current 2 goes down here, by Kirchhoff's first law, along here we'll have current 1 minus current 2. First, for the loop around the outside, like this, we can say that 2 volts, as we're passing through the top cell in the correct direction, minus 1.5 volts, as we go the wrong way through the bottom cell, is equal to current 1 times 20 ohms, the current passing through this resistor. We can rearrange, and we find current 1 to be 0.025 amps. This will be the reading on ammeter 1. Next, we can look at this loop around here. Next, we can look at this loop around here, which goes the wrong way through the cell and the opposite way to the direction we've shown the current here. So now we have minus 1.5 volts as we're going the wrong way through the cell is equal to minus 10 for the 10 ohm resistor times I1 minus I2, the minus sign as we're going in the opposite direction to this arrow. We can expand out the brackets, put in the value we've just found for ammeter 1, and simplify to give current 2 as minus 0.125 amps. This is the reading on ammeter 2.